my fellow assassins, to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. I want to welcome you all to the third year of the Dark Assassins podcast. Yes, it's kind of hard to believe, but we are officially now into year 3 of the podcast. And I wanted to start off this episode by letting you all know that I have officially sold my soul to the devil, because this podcast is now officially on YouTube. So after 2 full years, the podcast is finally on YouTube. So to all of you that are listening on YouTube, welcome. This podcast has been going on for a while now. Based on what I can tell, though, all of the videos or all of the episodes should also be on YouTube. So if you don't feel like actually going to a podcast app, you should be able to view all of them there. And if you're listening on YouTube, definitely be sure to subscribe to the channel. I'm not entirely sure what I'm going to be doing with this as far as the YouTube channel is concerned. The podcast is obviously going to continue. But the channel itself was mainly to kind of have another avenue to publish the podcast, although since it exists, I'll probably plan at some point maybe to do like some coding tutorials or home lab stuff or, kind of whatever I feel like. But there's definitely not going to be any kind of consistent upload, I don't think, unlike the podcast, which is generally, at least for the past 2 years anyway, basically been on a weekly basis. But yeah, that's the big news. I teased this a little bit a couple weeks ago when I mentioned I had some potential big plans for the podcast. I forget when that was. It was like 2 or 3 weeks ago. But yeah, that was what I was hiding. That is the plan. So you can go check us out on YouTube. We're Dark Assassins Inc. over there on YouTube. Or you could also click the link in the show notes below. Or you could go to our website, and there's a link there as well. And speaking of the show notes below, there's also a link to our contact at darkassassinsinc.com. So if you have any questions or topics for the show that you want answered, feel free to shoot us an email, or I guess if you're on YouTube, you can leave a comment, whatever works for you. And with all of that preamble and administrative stuff out of the way, let's get into this week's episode with our trivia question for the week. So this week's trivia question is Fortran was created in the late 1950s, but what company created it? So what company created Fortran? And that is your trivia question for the week. So last week, we talked a lot about the vulnerability that was discovered. Well, really not necessarily vulnerability, more just straight up backdoor that was discovered in the xzutils library for Linux systems. But the vulnerabilities just keep on coming because there was a new one discovered this week in the Rust programming language. Now, I haven't been the biggest champion of Rust here on the podcast. I haven't necessarily been like it's the best thing ever. I'm not a Rustation, as they call themselves. I'm not on the Rust bandwagon, but I also don't hate it either. To be quite honest, I've never really actually written any code in it. I mean, I've looked over code in Rust before, but as far as actually writing Rust code, haven't really gotten around to doing that. But the reason I bring this up is there is a vulnerability that's been dubbed Bad Bat Butt, and it's listed with a CVSS score of a perfect 10. So just like the vulnerability from last week with the XZUtils vulnerability, which is 100% a 10 because you don't even have to have password or anything. You literally could just connect to any system that's vulnerable via SSH and you're in. So that's obviously a 10. This one also scores a 10, but if I'm being honest, this isn't much of a vulnerability. But first, we should really look into what the vulnerability is. So according to the Rust Security Response Working Group that was kind of, I guess, looking into this, they said, quote, "The Rust standard library does not properly escape arguments when invoking batch files." And if you're unfamiliar, batch files is the .bat or CMD extensions on Windows. So the quote goes on, "Using the command API, an attacker able to control the arguments passed into the spawned process could execute arbitrary shell commands by bypassing the escaping." So essentially what this means is an attacker could pass malicious arguments into maybe potentially your program or command line arguments to your program that would then be passed through via the command API in the Rust standard library that would then be fed into a batch file as a command line argument, and you could potentially exploit arbitrary commands. So this is, I guess, technically, yes, it's a vulnerability, but at the same time, it's more of whose fault is it, right? Because on the one hand, yes, the Rust language itself isn't properly parsing the commands to ensure that you can't, actually add arbitrary commands by using escape characters to be passed into the batch file. But at the same time, you're also the programmer that allowed this to happen in the first place, because the Hacker News article even points out that this quote-unquote vulnerability exists in a lot of programming languages, and it's not just Rust. Specifically, some of the ones that it points out is Java, Go, Python, Ruby. I mean, some fairly large programming languages have this quote-unquote vulnerability in them by allowing you to pass potentially exploitable arguments into batch files on Windows. So it's not specifically just a Rust problem. Furthermore, the whole idea of passing unsanitized user input directly into a batch file via a system call, in this case through the command API in Rust, I mean, that's just one of the biggest no-nos in software development if you have even the slightest care about security. And it's not even strictly related to just batch files. It's any sort of system call, any kind of SQL query, literally anything dealing with user input. You should never assume that the input the user gives you is valid. You should always assume that the input given to you by the user is malicious until you can verify through your program that it is not. So until you have verified that that input coming in from the user is not malicious, or you have modified it in a way to ensure that even if it is malicious, it can't cause any harm to your program, to your database, to your system, whatever the case may be, you should not be doing anything with that user input. So I don't know how many times on this podcast that we've talked about, the importance of verifying and validating user input and always assuming it's malicious, but I've said it before and I'll say it again, under no circumstances should you ever do anything with user input until you can verify that it isn't malicious. So you could you could make the argument, I guess, that this is a programming language issue, but you could also very easily make the argument that this is a programmer issue. So this is kind of an instance where the skill issue argument that people like to throw around is actually a legitimate argument, in my opinion, because it's at quite honestly, it's something that if you've been writing code for any significant length of time, you should know better than to just pass in user input directly into a system call or an SQL query or literally anything without ensuring that it is valid and legitimate beforehand. So, on the topic of cybersecurity related things, let's get into this week's cybersecurity tip. So, harping back on a thing we touched on in last week's episode, I touched on this idea of OPSEC, or Operations Security. And this week's cybersecurity tip is kind of going to go into a little bit of what that is, but specifically that you should be practicing it. So kind of the idea of OPSEC, or Operations Security, is to ensure that you don't give out much, if any, kind of personal information at all. And the information you do give out, you ensure that you limit what information you do give out and who you give it out to. So if we look at some practical examples here. So first off, social media is, of course, very big these days. So the less personal info that you provide to the social media and just online in general, the harder it will be for advertisers to target you with ads, which may or may not be important to you. And it also limits the ability for threat actors to track you and to help mitigate what information they can get on you to help prevent them from exploiting you in the future. So, for instance, not sharing information like where you live, your birthday, contact info, all that kind of stuff can help prevent cyber criminals from using that data against you by potentially impersonating you. They could do this by, like, if they happen to know, where you live because you posted that online, and they know what your birthday is because you have that public on your Facebook account, they could quite easily potentially call up either a bank, a credit card company, a loan broker, whoever, and use the information they gathered on you because you made it freely available to impersonate you and potentially even steal your identity. But in addition to that, one thing that people commonly do specifically for passwords is they'll use some kind of personal information mixed into their passwords, which, if you're not using some kind of password manager that can randomly generate passwords for you and store them securely, I would recommend doing that because that would mitigate this potential vulnerability. But also, it is fairly common for people to do things like that with their passwords. Like, for instance, maybe they make it their dog's name and the year they graduated college or something like that, and kind of combine those two together to form a password. And on the one hand, it's easy for them to remember, yes, but on the other hand, if you know anything about that person, there's a chance that you have all the information you need to properly and accurately guess their password. So by not providing information like that online, you can help prevent potential things like that from happening. And in addition to that, you should also be cognizant of not only what you're sharing, but also the audience that is able to see it. Now, for as terrible as almost every social media platform is, at least most of them tend to at least have some sort of privacy features, and I use that term loosely. Of course, the privacy in this sense is other people seeing your stuff, not what the company can gather about you. Because if you think changing your privacy settings to have something set to only you, you can almost guarantee that the company that is providing that social media platform also has full access to that data as well and is definitely using it for whatever means they want to. But one thing that they are generally pretty darn good about is if you set, say, a picture or a post or some about information to be set to only your friends or followers can view it, or potentially even only you can view it, they generally, at least in my experience, respect that. And you can't, if you set, a picture of, say, you and your family on a vacation or something, to only your friends being able to see it, then some random stranger online wouldn't be able to see that image. So ensuring that you have the privacy settings set to what you want them to be set to is generally good practice. And it's also good practice to check those settings regularly because, things change. Maybe you initially were okay with a little more visibility, but now you're not. Maybe there are some new settings that got added or modified in your privacy settings. So it's definitely something good that you should regularly check just to make sure you're ensuring the people you want to see your stuff can see it and only those people can see it. So that is your cybersecurity tip for the week. Now let's move right along into what nerdy stuff have I been up to this week. So the past couple weeks I've been talking about the vector library I was working on, which essentially is implementing, at least partially, the standard template library vector from C++ and essentially making a C variant for it. So I finally got around to getting that pushed to my GitHub, and it honestly was, I pretty much had it done last week. It was more or less me procrastinating, trying to make sure the README and the make files were at least in an acceptable state, which I think I touched on in last week's episode. So got that pushed. And of course, I made sure to touch on the fact that it is compatible and works with MS-DOS and honestly pretty much anything that you can use a C compiler or has a C compiler that you can get running. Because as I mentioned, part of the goal for it was to write it in MS-DOS. So because the nature of it being written in MS-DOS, it has to adhere to in modern terms, an archaic version of the C programming language, specifically the ANSI C version. But that has the added benefit of basically being compatible with virtually every C compiler, because I'm also not using any operating system specific functions or headers or anything like that. It's only using the standard C libraries. So it's essentially, as far as I can tell anyway, completely compatible with anything that can compile C code. So if there's a C compiler for your platform, you can almost certainly get this library up and running. In addition to that, I also made some updates to my Server Connect program. So if you're new and you haven't heard about it, essentially what this project is it's a program I wrote, I don't remember how many years ago initially, and the goal of it was to essentially manage all of my SSH connections without having to use an SSH config file. And it'll manage all the connections for me, allow me to automatically log in like you would with an SSH config file, and basically replace that. And if I'm being honest with you, it's probably I don't know if I'd say my favorite program I've ever written, but I would argue it's the most useful program I've ever written, just because out of all the projects that I've written over the years, it's the one that I find myself using on the most frequent of bases. Like it's pretty much a daily use that I'm using this thing, and which is kind of why I've kept developing it and like adding new features, because pretty much the how this program gets updates is I realize I want it to do something that it doesn't currently do, and then I add it and then just continue to go about my day. And then if I find something buggy or that doesn't work, I fix the bug, push it, and just continue about my day. So that's pretty much how the development cycle works for this program. It's not like there's a set schedule of, okay, I'm going to plan on adding this new feature this month or anything like that. It's pretty much if I come up with something. So I did come up with some minor updates, which I had honestly been thinking about updating and implementing for a while, but it was never really that high of a priority. And it quite honestly isn't even that big of a priority anyway. The updates are quite honestly very minor. But the big updates, big in air quotes, I guess, updates is I added the ability to view the release notes for the current version you're on whenever you want to, and also the ability to reinstall the current version you're on. Now, the latter is more so for me than anything else, because seeing that I'm the one developing it, uh, potentially like pushing changes and trying to install the latest version, realizing there's an issue, and then pushing a change to fix that issue. I don't necessarily want to push a new version number, but if I don't, then I can't update. So I would basically have to reinstall it, and I'd have to do that more or less manually. So I was like, okay, I'm just going to write a feature that allows me to do that dynamically and just from the command line itself. So that was kind of the inspiration for that. In all honesty, it's probably not going to be very useful for the average user, but, it's at least there. And then as far as the video game I'm working on, I finally got back to working on that, seeing that I've been a little preoccupied the past couple weeks. So this week I finally actually started implementing the party screen interface. So as a quick recap for anyone that's new, my video game that I'm working on is essentially trying to recreate my own Pokemon game from scratch with pretty much developing everything from the ground up. And previously, I had the party screen, quote unquote, implemented, but it was essentially a glorified wrapper for the Pokemon summary screen that you could just cycle through the Pokemon in your party and see their summaries. So this week I finally actually started working on the actual interface that you'll be able to interact with the party menu. So you'll be able to switch Pokemon around in the future, give them items, take items away, click on them to view their summary and all that good stuff. So that is what I started working on this week, started laying the groundwork for. And yeah, that was about it. So with that, let's get into the main topic for this episode, which is kind of sort of in the cybersecurity realm, which is kind of how to deal with error handling in software projects and some things to do go in that realm. So first, I want to start with error propagation. So error propagation essentially is this idea of passing an error up the call stack to eventually be handled somewhere up higher up the call stack. So for instance, if you have a function that calls a function that calls another function, and the bottom function throws some exception or has an exception or an error code or something like that, that error code or exception will be passed back up the call stack until whatever function decides to actually deal with it. So there's a couple ways that you can handle this. One of them, as I mentioned, is throwing exceptions. So in some languages like Java, Python, for example, they have the ability for you to throw exceptions and then be able to handle those exceptions. So when you throw an exception, you can either essentially those errors will propagate up the call stack, kind of like I mentioned. And then whenever they're eventually caught, they can be handled appropriately by an exception handler. So, and for instance, one that I use quite frequently in Python is a keyboard interrupt exception handler. So, for instance, if you're in Python and you're running a script and you hit Control C, it'll kind of spit out a bunch of looks like error messages for the exception, right? So what you can do is if you had a keyboard interrupt exception handler, you can essentially catch those and be able to catch the Control C and be able to handle that however you wish. Usually I just ended up making it a clean exit so it doesn't spit out the error messages, and ensure if there's anything processing wise that's going on to terminate it and basically just exit cleanly. But of course, there are other exceptions that you could handle as well. Like, for instance, if you're using Java and you get the infamous array out of bounds exception, having an error handler to handle that exception so your program doesn't just straight up crash. And that's pretty much kind of the point of these throwing exceptions and catching the exceptions, is to prevent your program from crashing. Because if you're developing software that isn't specifically just for you, and potentially even if it is just for you, one thing that can be rather annoying is when you're using a program and then just out of the blue, it just crashes on you and you have to restart it, potentially losing progress in what you were doing, or even potentially corrupting data, as a potential worst case. So the ability to be able to throw exceptions when you encounter, things that are out of the ordinary, right? Going out of bounds on your array, for instance. Or getting a Control C input, for instance, if you're doing like some kind of command line process, being able to handle that appropriately and to prevent your program from hard crashing and saving off any data that you need to is definitely something that's very important to do. Now, in other languages where throwing exceptions isn't possible, another thing you can implement is error codes. So in languages like C, for instance, that don't necessarily have like the ability to throw exceptions, one thing that's very common is to have a return value, whether usually an integer of some kind. Specifically, I think the usual thing in C is you return 0 if, everything was fine. And then if everything was not fine, you return something else. So whether that's returning null or that's returning 1 or -1 or some other number to essentially indicate that an error occurred. And then if you're using something like an enum, for instance, you could have that as a list of all the various errors that could occur. And then you could do a quick lookup on that through something like a switch statement and identify what error occurred and be able to handle it accordingly. Because one thing that is definitely not ideal, especially in C that is not memory safe, is if you run into some sort of exception where, say, you weren't able to allocate the required memory, and what are you going to do? Now, I mean, you have a couple things you could do. You could just terminate the program. Might not be ideal, especially depending on what your program's doing. For instance, if you're a server, just randomly terminating the server is generally not a good idea. So you have to figure out a way to handle that error. So you can, if you say failed to allocate memory, you could potentially log that instance. That's something we're going to touch on here in a little bit. You could return some code back up the call stack, and then depending whenever you get to that upper case or the base case or whatever, you can identify that error occurred and either notify the user or, depends on really what your use case is. So that is kind of the benefit of error codes. You can, and one nice thing I guess about error codes, they're not necessarily as convenient as exceptions in the sense that you kind of have to make them yourself. But because you're making them yourself, you can basically design them how you want. but like I said, generally the most common way is to have functions that could potentially have errors occur, have a return code of some kind, and based on what that return code is, be, the error code. And then when you call that function, you can get that error code as the return value, and then based on what that return value is, handle said error accordingly. So that is another way to help prevent your program from just hard crashing. And I did touch on it a little bit briefly there. Logging is another thing that's definitely very beneficial when dealing with errors, because if you're, say, running a server, you're not going to have constant access to the console. So you're not always going to see what output it's generating. So being able to have any kind of errors or exceptions being sent to a log file is extremely beneficial for you to do some analysis afterwards to identify what function, threw the exception or had the error, what caused the error. Was it a memory allocation error? Was it a use after free error? Whatever the case may be, you can better be able to diagnose and troubleshoot those errors by having that outputted as a log file. And it's definitely also beneficial to log that too, for especially if you're like an end user. If you can log whatever errors happened, that's definitely going to be beneficial to send back to the developers for them to better identify what the potential root cause and take actions to try to prevent that potential error from happening in the future. So that's the first piece. So we have an error occurred, we detected it, and we sent it back up the call stack, whether by that was throwing an exception or setting an error code and logging the error. But then what comes next is you kind of have to deal with that, right? Like, an error happens. Generally speaking, it's not like the error is just going to happen in a vacuum and you don't have to worry about it. You generally have to do some kind of mitigation or recovery process when dealing with these kinds of errors. So depending on what the error is, you might have to recover to potentially a usable state, or depending on what the application is, it really depends on what and where the error occurs. But some potential things you can do as far as recovery goes is you can try to retry whatever failed previously, since sometimes if you had, say, a network issue, you're doing some kind of network-based programming and you had some kind of network failure, there's a chance that maybe if you're on Wi-Fi, your connection was spotty, and then if you retry it, it'll work fine. Or maybe your internet was down for a little bit there, so if you give it a retry, maybe it'll succeed. So potentially trying to retry a failed an error could potentially be the move, but again, it kind of depends on what it is. Like if you're dealing with a memory issue, that may or may not be something you want to retry, because if you tried to allocate memory and it failed for some reason, generally speaking, if you're trying to allocate memory and that fails, you usually have a bigger problem on your hands, generally speaking, not always, but usually. Now, granted, there potentially is the case where if you're, say, running a server or something, or you have an application that uses a lot of memory or is potentially multi-threaded, there is a chance that maybe you tried to allocate memory, it didn't work, but in the process of handling that error message and retrying to allocate the memory, maybe one of your other threads or one of the other processes running has recently completed, freed their memory, so you would actually be able to allocate the memory you wanted to initially, and a retry could actually work. So it is a potential option. Another potential option when dealing with errors is a graceful degradation, or essentially reducing the functionality of the system to an acceptable level, and essentially slowly degrade things that aren't necessarily critical features just to keep the program running until you can, say, maybe either reboot the system or restart the program. So this basically tries to ensure that your program remains operational and as functional as possible for as long as possible. So, for instance, if your program is say a network-based program, and it reaches out every so often to update some central server for progress it's done, and its networking capability gets knocked out for whatever reason, but you can still process whatever calculations you just can't upload them. That would be essentially a way of, this graceful degradation, or running in essentially a degraded state where you don't have the full functionality of the program anymore because you're not able to upload that data to the central server or whatever, but you're still able to do the computing on the device in the meantime, while you might not have the full operational state of your program. But whenever a technician or whatever comes along, they could reboot it or restart it or reconnect the networking or whatever the case may be. So yeah, those are some of the things that you can do. And then as the kind of the other point is defensive programming techniques. So how can you try to mitigate or prevent these errors or these issues from arising in the first place? And that kind of, touches on some things that we've already talked about even in this episode. Things like ensuring if you're dealing with user input, for instance, you're ensuring that it's good and valid and not arbitrarily passing user input into things. And generally, the idea of defensive programming is essentially anticipating potential errors you could face and potential failures that could occur, and writing and integrating safeguards to account for those and to potentially try to prevent against those and mitigate their impacts. So, like I said, input validation is probably one of the biggest ones. So, essentially ensuring that any data source coming into your program, whether that's a network connection, whether that's user input, whether that's a response from a database or an API call, whatever the case may be, you ensure that that data meets whatever you're expecting. So, for instance, if you're expecting an integer and the value you get is not an integer, you kind of need to be able to handle that. So, for instance, like if you reach out to say an API, a web API or something, and you're expecting a large JSON drop of data, and you get a 404, file not found error, like you got to be able to handle that somehow. So that's something that you should be expecting, in your input validation. That's different from, say, user input, but input validation nonetheless, of ensuring that the stream of data you're ingesting is actually what you expect it to be. And if it's not, you got to be able to handle that and potentially diagnose why you got that potential error why you potentially got that error. Was that a networking related issue? Was the query you gave the API invalid? Things like that. Another thing, bounds checking. So, if you're dealing with a memory unsafe language, this is even more critical, because in languages like C and C++ that allow you to access whatever memory you want and have buffer overflows, you need to be verifying your bounds. If you're dealing with a language that does have bounds checking and can throw exceptions like Java or Python, that would be something you'd also want to make sure you implement. So if you do run into a case where you get an out of bounds error, you handle that exception accordingly. Or you could even take the C and C++ approach and just ensure that the bound that, or whatever element you're trying to access, is actually within the bounds of the array, because the reason you really want to do that is, one, prevent buffer overflows, but also things like memory corruption and other security vulnerabilities. Because once you start allowing access to arbitrary memory, you're just opening yourself up to all sorts of problems, whether that's arbitrary code execution, whether that's, remote code exploitation, allowing the attacker to get a remote shell on your system. I mean, once you start getting into memory corruption and memory errors in general, it's a whole can of worms that you really want to ensure that you're protecting yourself against. And then another one, exception handling. So we kind of already touched on this one, ensuring that any time you do experience any kind of an exception or error or whatever, you handle it gracefully and you account for those errors to ensure that your application can remain stable and responsive, because again, the last thing you want is your program just to straight up crash. Now, as funny and as much of a meme as it is, especially on Windows, to get that infamous blue screen of death, as fun as it can be, if you're in the middle of working on something and you haven't saved your progress in a while, for instance, and you get one of those and now all your progress is lost, it's definitely not a fun experience. So as a software developer, one thing that you want to ensure is you handle those errors and those exceptions accordingly, so your program doesn't hard crash. Because if you're dealing with any kind of data that has to be persistent or be able to be accessed over multiple runs of the program, like any kind of user data, for instance, you want to make sure that even if the error that you experienced is like critical, like it's going to completely degrade the performance and usability of the program to the point that it's no longer functional, before you exit, you want to ensure that any kind of data that you had that hasn't been saved somehow gets saved off if you can help it. Because whether that's, dumping everything to a log file, or whether that's dumping all of any unsaved user input to like a temporary file or directory or something like that, then you can have your program on when it runs again, to be able to check, whatever that location is, to potentially be able to recover, from that error that you just encountered and caused your program to crash. And again, this kind of leads into the next point of ensuring you have that error logging and monitoring, because if you encounter any kind of error that's something you didn't expect, for instance, you want to ensure that you're capturing that to be able to track, where those errors are coming from. Maybe it's an edge case you didn't account for, or whether it's some nosy or malicious attacker that's trying to brute force their way in, or whatever the case is. You want to make sure you're logging that so you can identify those things and be able to potentially better defend against them or patch those issues to help prevent those impacts from affecting users. So the another thing, I guess, is essentially being able to detect these errors as soon as they occur and account for them and mitigate them, rather than letting them go up and up the stack, right? So being able to essentially, as soon as you encounter that error, dealing with it as fast as possible, because the last thing you want to do is have some kind of function that creates a like a JSON data structure or something, and somewhere all the way down at the bottom of the call stack encounters an error, and because of that, it propagates all the way up to the point where the data you get is just completely garbage, because every other call was relying on that one error and you were only handling errors at the very top. That would be potentially a large issue. So handling the error at the very bottom or as close to the source as possible is definitely the route you want to go, wherever possible, of course. Because in some cases, there's not a whole lot you can do if you're a utility function that, like, say, for instance, in C, has to allocate memory to do some kind of string manipulation. If that's just a utility function that fails, there's only so much you can do with that singular function, when in reality, other functions are going to be calling that function to do whatever they need to do. So, but as close as you can to the issue is where you want to handle that error, because again, if you're doing logging, for instance, you want to get it to as close to the source as possible, because if you just say, oh, I encountered an error in my init function, but your init function calls a bajillion other functions, if you could identify which function specifically in your init function encountered the error, that'll not only speed up your debugging process because you can, narrow down specifically what function you need to go to, but also it'll just make it more useful because you know where to go, right? Like just having an error in main is not as beneficial as, say, I encountered an error in logon validation, right? Because that's a lot more descriptive and I know exactly what function I need to go to, and I can, more easily identify what the error is, potential reasons why it could have happened, through the log files and that sort of thing, rather than just error in main. Because yeah, like I said, the closer you can get to the source of the fail, the better. So that was kind of a quick rundown of some techniques for dealing with errors and ways to defend against them and to recover from them. Because at the end of the day, kind of like I mentioned, regardless of if you're writing software for just yourself, whether it's like a personal project or you're part of a development team and you're writing commercial software, I think we can all agree as users of software, whether you're a developer or not, that something that's really annoying is when the program you're using just crashes randomly. And as we kind of touched on, these are some ways that you can prevent your program from crashing randomly. I think probably some of the biggest things that to take away from this is to think of how the program could potentially go wrong, and kind of those defensive programming techniques that we hit on at the end there and how to handle them. Because while you can throw all the exceptions you want and you can return all the error codes you want, if you don't handle them accordingly, what's the point, right? Like if you throw an exception and you never actually handle that exception and it ends up just crashing your program, I mean, you could argue what was the point of even throwing the exception in the first place. Now, granted, if it's something like in Java or Python and it was due to like an array out of bounds error, yeah, it's good that you threw the exception and just crashed the program rather than running into undefined behavior and potentially having some memory exploitation going on like you could in C and C++. So there is definitely merit to just, throwing exceptions, but you should also be trying to catch those exceptions as well and handling them accordingly. Same thing with error codes. If you're generating error codes, you should actually be handling them. Like if you throw, say, an error code that is supposed to define that like your memory allocation failed, you should actually somewhere be able to handle that use case, right? That your function returned not a normal state and be able to handle it. And that's kind of where, these defensive programming techniques come in, kind of anticipating potential errors, where they may occur, how they may occur, and trying to implement safeguards to ensure and potentially mitigate or prevent those from happening in the first place. And if they do happen, getting into that recovery phase, okay, so I got an error. What does that mean for the program? Can I even potentially continue? Can I not? Do I have to exit gracefully? Whatever the case may be. So just trying to put yourself in the mindset of, okay, how can this function fail? And kind of putting yourself in that mindset and getting in that defensive mindset, and how to better protect and safeguard from those potential failures happening. And again, if they do happen, ensuring you're adequately handling them. That is one way to help prevent your program from arbitrarily crashing. Now, of course, it's going to be almost impossible to catch every single edge case, or, you can't stop a cosmic ray from coming through and flipping a bit in your RAM, which then causes some completely undefined behavior in your program and causes it to crash. Now, of course, that is an edge case to be sure, and why things like ECC or error correction channel memory exist, or error correction code memory exists in servers, for instance, and workstations to potentially prevent against things like that, like bit flips. But as far as your program's concerned, if you get a random bit flip which causes some kind of corruption, I mean, there's really nothing that you can do. So of course there are instances that you can't necessarily account for, but trying to account for all the instances that you can and ensuring that you have, a lot of good test cases to account for all various different kinds of edge cases, the better you'll be. And the more of them that you can catch through your testing of edge cases like that, the better you can ensure that your program hopefully won't crash. And if you do ever run into errors, you can ensure that you're handling them properly. And hopefully this episode gave you some tools to ensure that you're doing that, and to hopefully allow you to do it better in your programs going forward. So with that, let's get back to our trivia question for the week before we wrap up this week's episode. So this week's trivia question was: Fortran was created in the late 1950s by what company? So again, what company created Fortran? If you said IBM, congratulations, you got this week's trivia question correct. And I guess anything like history of computer-wise, IBM, I guess, is almost always a safe bet because how early they were to the game. But yeah, in this case, they are the answer. And again, if you enjoyed this episode, definitely be sure to leave it a rating and review. If you're on YouTube, like, subscribe, all that good stuff. If you're on podcast, be sure to subscribe to the feed so you'll be updated when new episodes drop. And if you have any questions or comments for future episodes, you can shoot me an email at contact@darkassassinsinc.com. Again, the link is down in the show notes below, or if you're on YouTube, you can just leave a comment. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.